Welcome to the exam review of the Indian Actuarial Profession CT3 paper for November 2013. I'm John Lee, a tutor from ACTED, the Actuarial Education Company, which provides study materials and coaching on behalf of the UK and Indian actuarial professions. In this video, we'll give a brief overview of each of the questions on this paper. Whilst we don't provide detailed solutions for the Indian papers, we do offer a variety of online coaching, revision materials and study support, details of which can be found at the end of this video. So on to question 1. In part 1, we have to find the mean and median of a list of 5 data values. This should have presented no problems as long as you didn't forget to arrange the numbers in order before you found the median of 62. In part 2, we were given values A and B for Saturday and Sunday, and need to give the least possible value for the median of the whole week's data. To make it as small as possible, we would need A and B to be as small as possible, and the median of these 7 sets of values will be the fourth one, of 58. In part 2b, we're told we have the same mean and median as our answer in part 1. Well, we were given a mean of 60%, and so we know the total of these 7 values is 420. And from this, you'll be able to quickly work out that A add B is 120. To ensure we have the same median as part 1, which was 62, we'd need to have values of A and B that are on either side of 62. You now have to choose any 2 values of A and B that meet this criteria, for example 50 and 70. Part 3 is a quick comment about the dangers of inferring results from a single sample. Question 2. Test probability from Chapter 2. We have 2 urns with red and blue balls, but the number of blue balls in the second urn is unknown. However, we are told the probability that both balls are the same colour. A simple tree diagram will solve this. Here are the probabilities of selecting red and blue balls from the first urn, and here are the probabilities of choosing a red or a blue ball from the second urn using X to denote the number of blue balls. We're only interested in the probability that both balls are the same colour, which are the options indicated on the diagram. Totaling these up gives us a probability of 64 plus 6x over 160 plus 10x. And we're told in the question that this is 0.44. Solving this equation gives us x is 4. So we have 4 blue balls in the second urn. Question 3 tests probability functions and probability density functions from Chapter 3 of the notes. We first have to attain the probability density function of V. Now technically it's not quite a PDF, as V is what's known as a mixed distribution. Part of it is discrete, as we have an exact probability when V is 5, and part of it is continuous, where we have a PDF for the values of V greater than or equal to 6. It is given a value V equals 5 if it fails before time 3. So we simply have to work out the probability that t is less than or equal to 3 using our PDF. You could do this using integration, or by recognising it's an exponential distribution and using the CDF given on page 11 of the tables. To work out the PDF for the second part uses something called functions of a random variable from the end of Chapter 3. We are told that V is equal to 2t. And the steps of this method are as we write down the definition of the CDF of V, which is the probability that V is less than or equal to V. We then use the fact that V is equal to 2t. Rearranging this, we get a probability in terms of t, which we can find by integrating the given PDF from 3 up to a half V. As remember, it's only given this value if t is greater than 3. Once we've done this, we get the PDF by simply differentiating the CDF. For part 2 of the question, we have to find the expected efficiency value, i.e. the expectation of V. But remember, this is a mixed distribution. And so for the discrete part, you will do the value times its probability, and for the continuous part, we'd need to use integration. So we'll do the value times the PDF over the range of values that it takes. Although this question was a little messy, there was an example of a mixed distribution question in our X1 assignment. Question 4 was one of the trickiest questions on the paper, and is sort of based on Chapter 9 of the notes. Part 1 requires that we prove a result, but you'll only be able to do this if you know a clever trick, and that trick is to rewrite this expression here as follows. xi minus x bar, take away xj minus x bar. Expanding this out gives us the following. Now we take the double summation of each of these terms. The first term doesn't depend on j, and so we'll simply have n of the summation over I. The second term doesn't depend on I, and so we'll have n of the summation over j, which is just the same as n of the sum over I, as I and j are dummy variables. So we'll have 2n of the sum over I. The last expression's double summation can be split up as the sum over I times the sum over j, and each of these individual summations is 0, as we'd have sum of xi, which is equal to nx bar, minus nx bar, and similarly for the second part. And so now we need to divide by 2n times n minus 1. Dividing by the 2n gets rid of the 2n in front, and dividing by n minus 1 means we now have the definition of s squared given in the notes. Had you not known the clever trick, then you probably wouldn't have been able to even begin to prove this result. But where on earth in the notes would you get this idea from? Well, something similar is done in both Chapter 13 and 14 when we're proving the sum of squares relationship. But frankly, I suspect most students wouldn't have twigged this and will have moved straight on to Part 2. Here we have to show that we have an unbiased estimator. To do that requires us making use of the result that e of x squared is equal to the variance of x plus the mean of x all squared. While applying this to our xi minus xj squared, we have the following. We're told in the question that we have a random sample, and so xi and xj will be independent as long as I is not equal to j, which we're told. So we can split up the variance as the variance of xi plus the variance of minus xj, which will be the same as plus the variance of xj, because when we take a constant outside of the variance, we square it. Splitting up the means in a similar way gives the following. Now we're told in the question that the x's have a mean of mu and a variance of sigma squared. And so totaling this up, we'll have 2 sigma squared plus a mu minus a mu, which is 0 squared, so we just have 2 sigma squared, which is our required result. Now we have to prove that s squared is an unbiased estimator of sigma squared, i.e. we have to show that e of s squared is equal to sigma squared. On average, it gives the value we require. Well, e of s squared will be equal to our 1 over 2n times n minus 1, the sum of our expectation of xi minus xj all squared. Now when I is equal to j, then this will be 0, and so we can do the summation for I not equal to j. We now use the result that the expectation is equal to 2 sigma squared, and the result follows. Again, I suspect most students will have just simply pushed on to the next question. Question 5 tests convolutions from Chapter 6 of the notes. To help you, they've given the convolution formula. What they neglected to say is you should be integrating up to s and not to infinity. Substituting in our given PDFs gives the following. We're integrating from the start of our distributions, which is from 0 up to s. Now since we're integrating over x, anything which doesn't have x in it is a constant and so can be removed from the integral. This gives the following. However, to calculate this integral would require repeated integration by parts, which probably wouldn't be possible in our given time limit, and so the only feasible option would be to use a clever trick. That trick involves making it look like a beta distribution, u to the 17, 1 minus u to the 5 du. To do that requires first of all that we divide everything through our integral by s, and to undo this we'd need to multiply by s to the 22 outside. We then use the substitution u is equal to x over s. This then gives us an integral from 0 to 1. But since du is equal to dx over s, we'll also have an additional s outside. At which point you may go, we still have to use repeated integration by parts. Yes, we will, unless we swap this into an exact beta distribution, because then we're integrating over the full range of it, and so the answer will be 1. So we need to multiply by the following constant to match the formula given in the tables. However, we can't just add a constant, and so we'd need to multiply by its inverse in order to undo it. Don't forget all the other constants in front. Now, since we're integrating a beta distribution over the full range, that will give us the total probability, which is 1. And so our required probability density function is as follows. But without knowing the clever trick, I suspect most students wouldn't have got this far. And on to question 6, which tests compound distributions from Chapter 7 of the notes, and actually tests something called the individual risk model from CT6. Part 1 of the question asks you to write down expressions for E of S and the variance of S for a compound distribution. Given that this can be found in the tables, this would have been an easy 1 mark. Part 2 requires us to get the mean and variance of T. T is the total amount claimed on the whole portfolio from option 1. So that will be the sum of X1 up to X100, i.e. the total claims on policy 1 up to policy 100. Now we're told in option 1 that the number of claims on policy I has a Bernoulli distribution. Let's denote this by Ni. So if I want to know the amount of a claim on policy I, one of two things will happen. A Bernoulli distribution can only take two values, 0 or 1. So we'll have one claim with probability beta I, or we'll have no claims with probability 1 minus beta I. If we have no claims, then the total claim amount is 0. If we have one claim, then our claim amount will be whatever that claim is. Now we're told in the question the mean and variance, but we're not told anything else. I'm going to use YI to stand for the claim amount on the ith policy. Now the plan of action is we need to work out the mean of XI and the variance of XI. And because the policies are independent, we can simply total up the means and variances to get the mean and variance of T. Well, how do we get the mean of XI? Well, this is the clever part, which had you not studied CT6, you might not have got. XI is in fact a compound distribution, because we have a random number, 0 or 1, of random variables, yi. So we're just going to use our compound distribution formulae given in the tables that you quoted in part 1. E of xi will equal E of ni times E of yi. The mean of a Bernoulli with parameter beta I is beta I, and the mean claims we were told was mu. Similarly, for the variance, we'll have E of ni times variance of yi plus the variance of ni plus E of yi all squared. E of ni is the mean of a Bernoulli, which we said was beta I. Variance of yi is the variance of a claim, which we were told was sigma squared. Variance of ni is the variance of a Bernoulli, which is beta I 1 minus beta I. And then we need to multiply by the mean amount of a claim, which is mu, and square it. Now we have the mean and variance of xi. The mean and variance of t will just be the sum of each of these results. For part 3 of the question, we need to determine the mean and variance of t dash, where we have the number of claims has a Poisson distribution with parameter beta I. Well, there are two ways of doing this. We could follow the same approach as before, but using the mean and variance of a Poisson instead of the mean and variance of a Bernoulli, and the result will drop out very quickly. Alternatively, you could use the fact that when you add up a lot of Poissons, you get another Poisson. And so you could say that the total claims for a whole portfolio, n, is a Poisson with parameter sum of beta i's. And then just use the straightforward formulae for the compound distribution. Either way, don't forget to compare your answers, and you'll notice you'll have the same mean, but a different variance. And a little bit of algebra can show you which one has the bigger variance. Question 7, like question 4, was extremely demanding, and most students will have struggled with part 1, but hopefully could have used the given formula to simulate the values in part 2. The easiest way of doing part 1 is to spot a clever trick. Sound familiar? We are told that U has a uniform distribution on 0, 1. If we set V equal to U plus a half for values of U between 0 and a half, and U minus a half for values of U between a half and 1, then we can observe that this is also a uniform 0, 1. Let me show you. The values of the uniform distribution between 0 and a half will have a half added to them, and so they will go here. The values of the distribution between a half and 1 will have a half subtracted from them, and so they will go here. And so although we've swapped their order, we still have a uniform 0, 1. Now how does this help us? Well, to show that X has a standard normal distribution, there are two approaches you could do. One is to obtain the MGF of X and to show it has the MGF of a standard normal. And the second is to obtain the distribution function of X and to show it has the distribution function of a standard normal. Given that we are working with F in this question, which is the CDF, then the second method is the one we're going to go with, and this method is called functions of a random variable. Step 1 of this method is to get the CDF of X, i.e. the probability that X is less than or equal to X. Well, using the formula, that is the probability that minus the inverse of F, of our U plus a half or U minus a half, which we called V, is less than or equal to X. Multiplying both sides by minus 1 flips the inequality. Then inverting the function means we have the probability that V is greater than F of minus X, which is equal to 1 minus the probability that V is less than F of minus X. Given that V has a uniform 0, 1, the probability that V is less than F of minus X is actually just F of minus X. Now we're told that F is the CDF of the standard normal, and so F of minus X is the probability a standard normal is less than minus X. Well, since the standard normal is symmetrical about 0, the probability that it's less than minus X is the same as the probability that it's greater than X. And so we have 1 minus the probability it's greater than X, which is exactly the same as the probability it's less than X, i.e. F of X, or phi of X, if you prefer it in the posh format. And so we have shown that the CDF of X is equal to the CDF of a standard normal distribution. Since they have the same CDF, they must have the same distribution. Part 2 of the question requires us to simulate two observations. Well, it's slightly easier to do the second one first. Using that U is equal to 0.483, we will have that X is equal to minus F of minus 1 of 0.983, because we've added a half. Well, how do we do this? Remember, F is the CDF of a standard normal distribution. Since we're working out the inverse of the CDF, we want to find the value, which I'll call Y, which has a CDF of 0.983. Usually this kind of question we would use the percentage point tables. However, the examiners have cunningly chosen values that can be read off of the probability tables. You'll see that the CDF of 2.12 is 0.98300. And so the inverse of 0.983 is 2.12. However, don't forget your minus. Let's now do it for our second random number of 0.619. Using the formula, we'll need to subtract 0.5 from this. So X will be minus the inverse CDF of 0.119. So again, we want to find the value which has a CDF of 0.119. However, since this probability is less than 0.5, this will mean that Y is negative. So let's call it minus Y, and the value of y that we can look up will have a probability of 0.119 above it, which means it'll have a CDF of 0.881. Conveniently from the tables, we see the CDF of 1.18 is 0.88100, and so the value we require is minus 1.18. Again, don't forget the minus outside, and so our simulated value is 1.18. Well, after the nightmare question 7, we're now on to a much more straightforward question 8, which examines hypothesis tests and in particular the errors. A secret agent is investigating 2 nuclear power plants and has to determine the true number of weapon-producing nuclear plants, which is denoted by theta. And if any weapon-producing plants are discovered, then we're going to be invading. So our hypothesis is that there are no weapon-producing plants, i.e. theta is 0, or there are weapon-producing plants, i.e. theta is positive. In part B, we're asked to give the name of the error, that they do not invade A when some plants are producing weapons. So this means we do not invade, i.e. we believe that there are no weapons producing plants, so we think theta is 0, i.e. we accept H0, when in fact there are actually some weapon producing plants, so when it's false. This is what's called a type 2 error. The critical region are simply the values of x for which we reject the null hypothesis, i.e. we reject the hypothesis that it's peaceful only. Well, that will be quite simple. It'll be if we observe 1 or 2 of the power stations producing weapons. The probability of a type 1 error is the probability of rejecting the null hypothesis when it's true. Well, if it's true, there are no weapon-producing power plants. And we'll only reject it if our spy finds 1 or 2 weapon-producing power plants. Well, they're not going to be able to do that since there aren't, and so the probability of a type 1 error is 0. Question 9 tests maximum likelihood estimators from Chapter 10 of the notes. In Part 1, we have to show that S, which is the total number of head-head or tail-tail results, is equal to the following. This may have caused a problem unless you realise that 3 heads actually has 2 head-head options, and 3 tails has 2 tail-tail options. And so that gives us the 2A and 2H. For Part 2, we need to get the maximum likelihood estimate. That requires the likelihood, i.e. the probability of observing our sample. Well, we had A triple head results, and the probability of that occurring according to our model is a half of theta squared. And so, the probability is a half theta squared to the A. Similarly, we have B head-head-tail results, which have probability a half theta times 1 minus theta. So the probability of observing these is a half theta times 1 minus theta to the power of B, and so on. A little bit of work will show it is proportional to this result here. But don't worry if you didn't get it, you could simply take that result, log it, differentiate it, and get the maximum likelihood estimate, S over 2n. Don't forget to check it's a maximum. Part 3 of the question requires the asymptotic variance. Recall that the asymptotic variance is equal to the Kramer-Rao lower bound, the formula for which is given in the tables, as minus 1 over the expectation of the second derivative of the log likelihood. The only confusion that might have resulted from this is what is a constant and what is the random variable. Fortunately, the question tells us that E of S is equal to 2n theta, so it's the S which is the random variable. Everything else is a constant. This is very similar to finding the Kramer-Rao lower bound for a standard binomial question, and so shouldn't have presented a problem for well-prepared candidates. In Part 4, we have to calculate the large sample 95% confidence interval. This will be the standard theta hat plus or minus 1.96 times the square root of the Kramer-Rao lower bound. And since we're given data, we can work out what theta hat is. The last part has a slight twist. We're asked to test whether our model is correct, i.e. the probability of a head on the first toss is 0.5. There are a variety of approaches you could take with this. One is we could use a chi-square goodness of fit test. The second is that we could test whether the probability is indeed 0.5 using a hypothesis test of the binomial. Our null hypothesis is that the probability is 0.5, and our alternate hypothesis is that it's not. The statistic from the notes is x, which is the number of successes, minus np all over root npq, which will have an approximate normal distribution. But don't forget, you should apply a continuity correction, as we're approximating a discrete binomial distribution with a continuous normal distribution. And remember, the continuity correction goes towards the mean of np. Well, what is x? Well, x is the number of successes, i.e. the number of experiments which have a head on the first toss. This will be options A, B, C, and G. So adding these up gives us x is 516. We did 1,000 experiments, and our null hypothesis is that p is 0.5, so np will be 500, and so for our continuity correction we'll need to subtract a half from 516 to make it closer to the 500. This will give you a test statistic of 0.980, which is not significant. Question 10 is a gorgeous, straight down the line question on analysis of variance from chapter 14 of the notes. There really should have been absolutely no bother whatsoever with this question. Part 1 asks us to comment. Don't forget to state the obvious things about the mean is decreasing, and also note that the first and last results almost don't cross over, which means it's almost certain that the means are not the same. Part 2 requires us to state the assumptions, i.e. each of the treatments are normally distributed with the same variance, and if you want, you could mention that observations are independent. Part 3 is carrying out the analysis of variance test, and you'll simply use the formulae given in the tables to show that it is indeed significant. The last part asks us to carry out an analysis of the mean differences using the least significant difference approach. This will require arranging the sample means in order, and then carrying out a two-sample t-test on each pair. What you'll discover is the first two have no significant difference, and so we underline them on the diagram. B and C have no significant difference, and C and D have no significant difference. However, all other combinations do, and so you'll have the following diagram. Question 11 is a very straightforward question on correlation and regression from chapter 13 of the notes. Part 1 requires you to obtain the least squares fitted regression line, so you have to calculate the intercept parameter alpha and the slope parameter beta, and then your fitted regression line is alpha hat plus beta hat xi, where we obtain the alpha hat and beta hat using the formulae in the tables. Part 2 is a 95% confidence interval for beta, stating the assumptions made. Well, the only assumption is that it's the normal linear regression model, i.e. we assume that the error terms are normally distributed. Other than that, it's straightforward. Part 3 asks us to use the fitted model to construct a 95% confidence interval for the mean IBM share price. So we're doing a confidence interval for the mean response. Whilst this is a little bit messy, it is very standard and should have presented no problems whatsoever. And finally, question 12 is a little question on hypothesis tests from chapter 12 of the notes, in this case testing the mean battery life. Our null hypothesis is that the mean battery life is what it used to be, 300 minutes, against the alternate hypothesis that there's a reduction, i.e. mu is less than 300. Our statistic is x bar minus mu over sigma over root n, because we are saying this question that we know the true value of the standard deviation of batteries. Calculating this will give you a statistic of minus 2.582, which is less than the 1% critical value, and so we have sufficient evidence at the 1% level to reject the null hypothesis. For further information on the support we offer our Indian students, please go to our website www.iai-ct3.com. www.acted.co.uk/India. There you'll find details of the revision materials we offer, as well as online tuition, whether pre-recorded or live. On the screen now are links to a YouTube video of a unit from our CT3 online classroom, and also a video snippet from one of our live webinars. Both products come with full tutor support and are available in pounds or rupees from our e-store.